Hello viewers, welcome back to our channel. Today we are here to discuss another important lecture of field theory. In this lecture we will present a beautiful theorem which give you the idea that up to an isomorphism there are only two prime fields. One is finite field, that is Z by Pz, and another is infinite field, the field of rational number. This is also a prime field. So up to an isomorphism there are only two fields. One is finite and another is infinite. So we will give the systematic proof of this theorem. So let's start the proof. But before going to the proof, I will show you the breakouts of the proof. It means the steps you have to remember to learn the proof. And with these steps, you will never forget the proof of this theorem. So students, before going to the proof, we will discuss the important steps. And if you remember these steps, then your proof will be easy and you will never forget the proof. So if you know that, we have to show that if P is a prime field, then either P is isomorphic to Q or P is isomorphic to Z by Pz. Okay. So if you focus on this, then it gives you the idea that first we have to define a map from Z to P. So first step will be to define a map from Z to P, the set of integer to the prime field P. Okay, so first step will be to define a map from Z to P. Second, we will prove that this map will be a homomorphism of rings. Okay, then you have to find out the kernel of this map, and if you find the kernel of map, then fundamental theorem says that Z by kernel theta is isomorphic to the image of theta. Okay, so this will be the important step using the fundamental theorem of homomorphism. After finding out the kernel, you have to discuss two cases separately, that kernel is 0 or non-zero. According to these two cases, you will get the two different choices. Okay, so we will separate these two cases separately. First we will discuss when the kernel theta is 0 and when kernel theta is non-zero. Okay, while using this concept kernel theta, you have to use the fact that isomorphic integral domains have isomorphic field of quotients, and this is very crucial steps in proving this theorem. So if you remember these steps, then you will never forget the proof of this theorem. So let's start the detailed proof of this theorem. तो चलिए स्टार्ट करते हैं प्रूफ को. सो सबसे पहले देखिए क्या है. व्हाट इज गिवन टू यू, लेट P be a prime field. P be a prime field. Okay, so what is our claim? Claim is that we have to show that either P is isomorphic to Q or P is isomorphic to Z by Pz. It means in every situation we have to define a homomorphism. Okay, so what we will do, we will define a map theta from the set of integer, the ring of integers to P. So how will you define? What is the natural way to define a map from the set of integer to a prime field P? You know that P is a field. P is a field. So I will give you the idea how to define a map. Okay. So multiplicative identity is there because P is a field. There is a multiplicative identity in P, and P under addition is abelian group. It means if you add E plus E plus E as you wish. Okay, so you can add E up to how number of times, and then that will give you the element of P. Okay, so this will be the idea to define a map from Z to P. Okay, so if you choose integer from the set of integer, so define a map theta will apply on the set of integers. and if it will give you ME, that is E plus E plus E, how many times? M times, and it will give you ultimately an element of P. Okay, as we have discussed here. Okay, so this is the natural way to define a map from the set of integer to a field P. Okay, now we will prove that this map is a homomorphism of ring. So what is our claim now? This map theta is a homomorphism of rings. So to prove that this is a homomorphism of rings, what we have to do, we have to show that theta separates addition and theta separates multiplication. Okay, so let for this choose two element m and n from integers. Okay, so what we have to show that theta will separate in addition. Theta preserves the addition. Okay, you can say that. Okay, so by the definition of map, what you can say that theta of m plus n, because m is integer, n is integer, therefore m plus n will be an integer, and by the definition what it will be, m plus n times e. Okay, and you are very much clear that m plus n times e means, that is, you can write this as me plus ne. Okay, now, and what is this? This is theta of m and this is theta of n. So there is no problem to say that theta preserves the addition. Okay, now we will see that how it will preserve the multiplication. Okay, again theta of m into n will be, by definition mn is an integer. Okay, so it will be mn times e, but you know that e is the multiplicative identity, so you can write e as e square, because e square is again e, because identity element is idempotent. Okay, so this will be e square plus e square plus e square, how many times? Mn times, mn times. This is a very important step. So you can write this as e square plus e square plus e square mn times. Okay, now here there will be a trick that you can write this as e plus e plus e times e plus e plus e. Here you can write this as m times and this is n times. And if you see that if we open the bracket, then every time you get e square. If you open these two brackets, every time you get e square, and what are the number of these e square? These are mn. Okay, so there is no harm to write this expression as this. Okay, and what is this? This is m times e, and the second factor is n times e, and ultimately we get theta of m into theta of n. So what we have seen? We have seen that theta preserves additions and multiplication, therefore theta is a homomorphism of ring. So this is the conclusion: theta is a homomorphism of rings. Okay, so we have completed two steps of the proof. First we define a map, secondly we will prove that theta is a homomorphism of rings. Now the third task is to find out the kernel of theta. So now, by fundamental theorem of homomorphism, since the map is from Z to P, therefore Z by kernel theta, this is the quotient ring, that is isomorphic to image of theta, and this image of theta is contained in P. Okay, or you can write this as Z by kernel theta is isomorphic to image theta. You can write this as theta Z is contained in P. Whatever you want, you can write this. Okay, now what is our focus? Our focus is on kernel theta. Now kernel theta, because theta is a homomorphism of ring, kernel theta is an ideal of the ring of integers. and you know that the ring of integer is a PID. PID means principal ideal domain. Therefore, every ideal is generated by a single element. This implies there exists some M belongs to Z such that kernel theta, because Z is PID and kernel theta is ideal, therefore it will be generated by a single element. Kernel theta is generated by M. Okay, so this is the kernel. Now this equation, call this equation star. You can rewrite in the preview of this one, rewrite star as Z by mz, because kernel theta is mz, is isomorphic to image theta, and image theta is contained in P. Now kernel theta is generated by m. M is an integer, so we can discuss two cases here, if m is 0 and if m is non-zero. Now kernel theta is mz ideal generated by m. So we can separate here two cases if m is 0. First case is if m is 0 integer, then kernel theta is nothing but 0 ideal, and therefore z by mz is isomorphic to z by 0 ideal, you can say, or it is isomorphic to z. It means this factors turns out to be just simply z. Okay, so this implies z is isomorphic to image theta. Image theta means theta of z, and it is contained in P. So this steps comes from this one. Okay, now explore this step. Z is isomorphic to theta z, and theta z is contained in P. Okay, now here comes the important concept of integral domains. Okay, since you know that the set of integer is an integral domain, integral domain, and theta z is isomorphic to z. Theta z is isomorphic to z, and this implies theta z is also an integral domain. It means we have two isomorphic integral domain, one is z and second is theta z, image of z. Okay, so we have two isomorphic integral domain, and we have stated an important result that isomorphic integral domains have isomorphic field of quotients. So this implies z and theta z are isomorphic integral domains, and therefore z and theta z have isomorphic fields of quotients. So let me throw some light on the concept of field of quotients. Okay, however, this is a very important and separate case, but let me show you some glimpses of the field of quotients. So if you have any integral domain D is integral domain, then the set of elements of set of quotients of D, A by B types element, B is non-zero, and A and B belongs to D. So set of quotients of elements of D forms a field and it is called field of quotients. It is called field of quotients. Okay, so if D is an integral domain, collect all elements in this form A by B. A and B are the elements of D. These elements are in form of quotient, and the collection of all these elements is a field, and it is called field of quotients. So from here you can see that if we take Z in place of D, because Z is also an integral domain, so what is the field of quotient? Any guess? You can say that the field of quotient of Z is Q, because you know that every rational number is of the form A by B, and A and B are integer. So if Z is integral, you say that Z is integral domain, then what is the field of quotient of Z? A by B, rational numbers. Okay, so let we assume that Q1 and Q2 be fields of quotients of Z and theta Z respectively. Okay, so what we have assumed? We have assumed that Q1 is the field of quotient of the ring of integer, and Q2 is the field of quotients of theta Z. But there is an important thing about the field of quotient, that these field of quotients Q1 and Q2 are smallest fields containing Z and theta Z respectively. So if you say that it is a field of quotient, then it is the smallest field containing the integral domain. Okay, so Q1 and Q2, these are the smallest field containing Z and Qz, and you know that P already containing these Z and theta Z, and these are the smallest. Q1 and Q2 are the smallest, so you can say that Q1 is isomorphic to Q2, and being smallest, these are contained in P. Okay, so we have this result. Now because Q1 is the field of quotient of integer, so it is nothing but it is a set ring field of rational numbers, is isomorphic to Q2. Q2 is contained in P. Let me correct this. So Q is isomorphic to Q2. Q2 is contained in P, but we have assumed that P is a prime field. P is a prime field, so it cannot contain a subfield. Okay, so this implies Q2 coincides with P. Q2 coincides with P, and this implies Q, you can replace Q2 by Q, because Q is isomorphic to Q2. Q is isomorphic to P. So what we have proved, that in first case, if you see that M is 0, okay, then the prime field is isomorphic to the field of rational number. So this is the first case. Now we will prove that if you assume that M is non-zero, then you will find that P is isomorphic to the finite field Z by Pz. So let's consider the case if M is non-zero. Okay, so if M is non-zero, then M can be assumed as positive integer. Okay, so it is an exercise for the audience, that if M is non-zero, you can assume M to be positive, and there is no harm in considering M to be positive. If you have any idea about this fact, then write in the comment section box, and if you have no idea why M can be taken as positive, then you can ask me through the comment section box or email. Okay, so M can be positive, and this implies M greater than equal to 1. Now we will rule out the case when M is equal to 1. It means M cannot be 1. We will now prove that M cannot be 1. Suppose M is equal to 1. Okay, since kernel theta is generated by M, this implies M belongs to kernel theta. And if M is 1, If m is 1, this implies m belongs to kernel theta. Now you can say that theta of m is 0, because any element belonging to kernel theta give you the value 0. Okay, now theta m means me is equal to 0, and if we assume that m is 1, then 1 into e is equal to 0 implies e is equal to 0. Multiplicative identity is 0, which is a contradiction. Okay, if you assume that m is 1, then you get identity e as 0, which is a contradiction. So m cannot be 1. M cannot be 1, and this shows that m is greater than equal to 2. Okay, next we claim that if m is greater than equal to 2, then m must be prime number. So now we claim that m must be prime. Again we will prove this by contradiction. Suppose m is not prime. This implies m must be composite. And this implies you can write this m as product of two non-trivial factors. So m can be written as m1 into m2, 1 less than m1 less than m, and 1 less than m2 less than m. Since m is in the kernel, therefore theta of m is equal to 0, and this implies theta of m1 m2 is 0, and this implies m1 m2 e, because image of m1 m2 under theta is m1 m2 e, is 0, and again rewrite this as m1 m2 e square. You can write e as e square because e is a multiplicative identity, and this implies m1 e into m2 e, because everything is happening m1 e, m2 e, these are the element of the field p, and p is a field commutative ring under multiplication. So you can write m1 m2 e square as m1 e m2 e is equal to 0, and all this happening in p, and p is an integral domain because p is field, p is integral domain, So if the product of two element is 0 inside p, then either m1 e 0 or m2 e 0. It means either m1 belongs to, or you can write one step more, you can say that theta of m1 is 0 or theta of m2 is 0. It means either m1 belongs to kernel theta is generated by m, or m2 belongs to kernel theta, which is again generated by m. So this implies either m divide m1 or m divide m2. Okay, which is not possible. Because why it is not possible? Because m1 is greater than m is greater than m1, and similarly m is larger than m2, so m cannot divide m1 and m2. This is a contradiction, and this contradiction proves that m cannot be composite. So this implies m must be a prime integer. So again, the equation star, if you keep in mind that what is the star equation, z by mz kernel theta is isomorphic to theta z, and that is contained in p. Now what is m here? M is prime, because we have proved that m is prime. So z by pz is isomorphic to theta z, and theta z is contained in p. So it means this theta z is isomorphic to a field of p elements. This is a field of p elements. So theta z is a field of p element. You can say that theta z is a field of p elements. So this implies p contains a field isomorphic to isomorphic contained a field isomorphic to z by pz, but p is prime, so it cannot contain a smaller field. So this implies z by pz is isomorphic to p itself. Because p is a prime field, it cannot contain a smaller field, therefore p is isomorphic to z by p itself. So from this we can say that, what is the conclusion of the theorem? Up to an isomorphism, there are only two prime fields. One is finite, that is z by pz, and second is infinite, that is the field of rational numbers. Okay students, so this completes the proof of this theorem. Hope you have learned a lot from this theorem. If you like the content of our channel, please share and subscribe. Thank you. Stay tuned for upcoming lectures. Thank you.